Okay, welcome everyone to Math 128. So I think everyone's good today. Yes, so we had one lesson before. I don't remember what we did, but I'm presuming that we just covered the introductory material to the course. All my lessons kind of blend together because it's all the same classes and it's all the same material. So today we're going to start on 1.1, the first chapter. So the first chapter is basic arithmetic, which means like dealing with addition, multiplication, subtraction, along with numbers. That's basically what basic arithmetic means. So the first section is Introduction to Fractions. And I just got to make sure, okay, so recording is still good. Let's share screen. Does anyone have any class-related questions before we start? Okay, let's start. Oh, and someone did ask, people who are just watching the recording will be confused about this, but I was just showing everyone my snakes. Someone asked how expensive they are, but note that they live for like 20 or 30 years. So they're a pretty good investment considering how long they live. Ooh, and here's a fun fact, and then we'll finally get to the math. I recently found out, and I'm going to sound like a weird person saying this because it sounds so wrong, but I looked it up and it's apparently correct. Did you know that modern birds are closer to crocodiles than crocodiles are to other reptiles? That's badass. I never knew that before. Birds are really, really closely related to reptiles. Birds are basically the descendants of dinosaurs, more or less. They're pretty much similar to what dinosaurs would look like. So I thought that was pretty cool. So if you have a pet bird, your bird is closer to a crocodile than a crocodile is to reptiles. Or other reptiles, I should say. Okay, let's do some math. Hopefully everyone is excited. And let me know if I'm sharing my screen and you can't see it, just of course, let me know. And if I forget to do the recording, please let me know as well, because I always forget things. Okay, so introduction to fractions. So we're just going to go through basic stuff with fractions. I'm not going to assume that anyone has any prior knowledge on fractions. So we just kind of start from the ground up. Okay, so let's see, a fraction. What the heck is a fraction? A fraction means splitting something into parts or fractions, as they say. I just did some air quotes. For example, slicing up a pizza, cutting a pipe into length, mixing a drink. So it's all about dividing things up into equal parts. And when we're talking about fractions, it's always equal parts. Okay, so fractions have two parts, of course. They have the top part and they have the bottom part. Top part is called the numerator, and the bottom part is called the denominator. So the denominator is how many parts make up the entire whole, and then the numerator is how many specific parts you have of those. So for example, if you have, hold on, here it is. If you have like 1/8, that means that, for example, you took a piece of pizza, you sliced it into 8 slices, and then you took one of those slices. So try to remember that numerator is on top, denominator is on the bottom. Try to remember it however way you can. For some reason, the way that I remember it is I just think of the word and then that should be a D right there. And then it's kind of like you got the N and you got the D, and that's how I remember it. It's a silly way of remembering it, but that's how people remember things. Usually it's more helpful to have like a reference or a memory device or something like that. Okay, so in this case, it says, what are the numerators and what are the denominators here? So of course, these are pretty easy questions. For the first one would be the numerator, 2 would be the denominator, et cetera, et cetera. For the last one, same thing, 1,000 would be the numerator and 7 would be the denominator. So it doesn't matter what's bigger or what's smaller, it just matters what's on top and what's on the bottom. Okay, so there's a couple of different types of fractions. The first one is a proper fraction. So that's a fraction that is less than 1. So I guess it's kind of logical that they would call it a proper fraction, but I mean, like, it's not any less proper than any other fraction, but that's what they call it. So less than 1, so in that case, the numerator will be less than the denominator. So an example of a proper fraction would be 1/3. And then an improper fraction, as you could probably guess, is where the number is greater than 1. So therefore, the top number will be larger than the bottom number. So an example of that would be 4/3. So that's an improper fraction. And then you have mixed numbers as well. So that's where you have a whole number component, and then you have a fractional part of that as well. So there's the three different, there's other ways of categorizing fractions as well, but those are the most basic ones. Okay, so now we're going to learn about reducing to lowest terms. So this part is a bit of a prelude. So if you look at any given fraction, there are technically infinitely many versions of those fractions that are all the same. So for example, if you have 1/2, you could write this in many ways. You could write it as 1/2, that's the simplest way. You could do a 2/4, you could do a 3/6. You could do, if you're feeling really adventurous, you could do 1,000/2,000. And obviously it goes on forever and ever. So we always want to deal with, someone said 8 out of 16. That's also, that's 1/2 as well. So yeah, infinitely many different iterations of these fractions. But you know, if you had 1 trillion over 2 trillion, there'd be no point in dealing with 1 trillion over 2 trillion. It would be easier just to deal with 1/2. So we always want to kind of deal with the simplest version of a fraction. And if you have stuff like this that's kind of in these larger forms, you can always take them and reduce them so that they're their simplest form. So like all of these can be reduced back to 1/2. So that's what we're going to learn in a minute. It's reducing something to lowest terms so that it's in its simplest form. And here's just an example illustrating why all these fractions are the same. You see half of a pizza, of course, that's the same as 2/4 of a pizza, same as 4/8 of a pizza, same as 8/16 of a pizza. So yeah, they're all the same. So before we go to reducing to lowest terms, we need a definition. And the definition is the definition of a factor. So factors are numbers that we multiply together to get other numbers. So here's the simplest example I could think of. 2 times 3 equals 6. So 6 has factors 2 and 3. Another one, a number that has a ton of factors is 12. So 12 has factors. So basically, again, they're numbers that you multiply together to get other numbers, or you could also think of them like in regard to 12, you could ask yourself what divides evenly into 12? Like what would divide evenly and give you like a nice whole number? So 12 has factors, it has 3, it has 4, it has 2, it has 6, and then it has its trivial factors. It has 1 as a factor, and it has itself as a factor. Every number has 1 and itself as a factor, because like 12 divided by 1 is 12, so that's a whole number. 12 divided by 12 is 1, that's a whole number. So yeah, every number has those 2 trivial factors, I guess you could call them, 1 and itself. And then most numbers have other meaningful factors. Of course, 12 has a ton of them. And yeah, there are numbers called prime numbers that don't have any meaningful factors. Basically, nothing really divides evenly into themselves. An example of a prime number would be 7. So like if you divided 7 by 2 or 3 or 4 or 5 or 6, none of them would give you nice even numbers. So 7 only has its trivial factors, which are 1 and 7. So yeah, prime numbers only have just those trivial factors. Prime numbers are very interesting. They're technically the building blocks of numbers. Like if you took any given number and you broke it up into its factors, and then you just kept breaking up everything, it eventually they would all be prime numbers. Every number is constructed of prime numbers. It's like the atoms or the molecules of numbers. And there's also a really, oh, I could see, I'm just getting distracted by my snake. He's trying to escape from his box already. He's checking literally every centimeter of it and pushing up against it to try to get out. It's okay, banana. Okay, prime numbers are very, very interesting because I believe there is, let me just double check this. There are these things called the Millennium Prize problems. They are math problems that if you solve one, you get $1 million. Originally, they did that when it turned into the 1900s. There was a famous mathematician called David Hilbert who posed a bunch of math questions. And then when it turned to the 2000s, they came up with the Millennium Prize problems, which are a bunch of math problems that people are trying to solve. How do you spell millennium? This is tough. I mean, I'm writing a book and I still can't spell. I'm just going to put prize problems. Problems. Okay, I'm going to have to use Google for this. Millennium prize problems. So I think one of them are concerning prime numbers, if I'm not mistaken. I have a notoriously bad memory, so don't quote me. Yes, the Riemann hypothesis. There's a thing called the Riemann hypothesis that tries to figure out how the prime numbers are interspliced through the number line. Like, is there a formula for like, where the, oh, sorry, am I sharing this? Let me reshare this. Share screen. Yeah, the Riemann hypothesis. Yeah, so it's a conjecture about how the prime numbers are distributed throughout the number line. So if you solve this, you get $1 million, which, I mean, to be fair, isn't even really that much money these days. But yeah, the Millennium Prize problems are pretty cool. There was a mathematician, I think, who thought he solved this, but he was mistaken, and that was a mathematician called Ramanujan. So prime numbers are interesting, and they have, for some reason, they have giant supercomputers running prime numbers 24/7 to try to discover the newest, largest prime number. So people do stuff like that for whatever reason. Okay, let's keep going. Okay, share this. So those are factors. So let's do one more example. Like, let's do factors of 100. So what would be some factors of 100 if anyone wants to jump in and name some?
50 times 5.
Sorry?
50 times 2.
Yes, exactly. So its factors are 50, also 2. What else? And any factor of a factor will also be a factor. Someone said 1 in 100. Exactly, yes.
25
1 in 100. What was that? Oh, I thought
25. 25.
25, exactly. And there's a bunch of other ones. So yeah, we got 1, we got 2. What else? Is 4 a factor? Yes, 4 would be 1. 5 would be 1. 10. 20. Geez, that's a lot of factors. And then every factor of 20, but we already have those. We got 50. So is that all of them? Yeah, you'd have to check the factor of each factor to see if those have factors, because each of those will also be a factor of the original number. 20, yep, we got 20. Let's see, 25, 2, 5. Yeah, that seems like all the factors for 100. So those are factors. So factors are important for reducing fractions to lowest terms. Okay, so here's a definition. A fraction is said to be in lowest terms if the numerator and the denominator have no common factors. So what does that mean? Well, let's look at 2 examples. Here is 2/3, and here is its equivalent factor, its equivalent fraction, 6 over 9. So you notice that 6 and 9, they each have a common factor. They each have a common number that would hypothetically divide into them. 6 has a factor of 3, and 9 also has a factor of 3. So there's kind of like a 3 stuck in there, and that kind of, in this case, it is not in lowest terms because it has this common factor that is in the top and the bottom. On the other hand, 2 over 3 is in lowest terms because 2 and 3, they have no common factors. Like the only thing that divides into 2 is just 1 in itself, and obviously none of those divide into 3. So that's like, it's like a technical definition, but that's how you know if something is in lowest terms or not. You basically look to see if you have any of these hidden factors lurking around in your number. And then later on, we're going to learn how to remove them, and then that'll reduce something to lowest terms. So let's see how we do that. Okay, so to reduce a fraction to lowest terms. So we'll go through like the general procedure, but then we always do like a million examples. So just bear with me. So what you do is you look at the top number and you look at the bottom number and you ask yourself, is there anything that divides evenly into both of these numbers? Do they have any common factors? And then what you do is you divide both the top and the bottom by that number. And then you just keep going and going until you can't go any further and until it's in lowest terms. So you're basically just like pulling out factors that are common to the top and the bottom and just tossing them away. So let's look at how we do that. So here is, I think I'm going to switch to a whiteboard. Okay, whiteboard. And anything that I do on the whiteboard is in the PowerPoint, and anything in the PowerPoint has solutions included, just because I thought people would get frustrated otherwise. So first one is 12 over 16. So you ask yourself, what factors does 12 have? What factors does 16 have? Do they have any common factors? So let's check the chat. So someone said 4. Perfect. Yes. So 4 divides into 12, and 4 also divides into 16. So someone said 4, and then someone said 3. So in this case, it's going to be 4 because 16 is not divisible by 3. So in this case, our common factor is 4. So what you do is you divide the top number by 4, you divide the bottom number by 4, and then you see what you get. So the top number is 3. Actually, when the person wrote 3, that's probably what they were referring to. And then 16 divided by 4 is 4. And now it's in lowest terms. So that's always the procedure. And for the factor that you're going to take out of your fraction, always pick the biggest number possible. In this case, you could have taken a 2 out of it, and that would have reduced it to 6 over 8. But then you got to keep going because it's not quite in lowest terms. And in that case, you'd have to take another 2 out of it. And it's like, why am I doing that? Why don't I just do a 4 and then I don't have to keep doing it over and over again? So always use what we call the quote, largest common factor, end quote. Okay. So what else do we have? And there's a couple of actually, before I was going to go through the common mistakes that everyone makes with these, but we'll do a few more examples. Next one, 40 over 50. So this one's a pretty easy one. So what would be the largest number that divides evenly into both of these? Let's see, 10, exactly, yes. So we divide by 10, divide by 10, and we get 4 over 5. In this case, if it was me, what I would do is I would just scratch out the top 0 and scratch out the bottom 0, and then that's just a quicker way of doing it. You can do that as long as you scratch out the same number of zeros on the top and the bottom. That's basically like the one fundamental rule of math you have to remember, is that you just have to keep everything balanced out. If you alter the top of the fraction, you have to alter the bottom in the same way. Otherwise, you're changing the overall value of the fraction. So a couple of things you have to note. You have to divide by the same number on the top and the bottom. Sometimes I see people dividing the top by 10 and the bottom by 5, and it's like you can't do that. The whole point of taking the same number out is, first of all, you're reducing it, but second of all, you're maintaining a consistent value for your fraction. Just like when you have an equation and you have to treat each side the same, it's similar to that. So just make sure it's always the same number. Make sure it's always a factor of both numbers. What other mistakes do people make? It seems like there's only a limited number of mistakes that one could make here. And of course, there's arithmetic mistakes. So, you know, if you're bad with arithmetic, which is just like basic adding and multiplying and stuff, then use a calculator. I'm very bad at arithmetic. Yeah, so if I make any arithmetic mistakes, feel free to let me know. I won't be embarrassed. I'm very bad with numbers and addition and subtraction, but I'm good with like advanced geometry and topology and weirder abstract stuff. So let's see what else we have. And please practice these on your own. Usually I would give a couple examples and have people try them, but for an entirely online class, it's a bit, I don't know, it's a bit weird. Okay, so I'm just looking at the slides, and it just reiterates that you always want to use the largest common factor. So always take out the largest number that you can. So let's do a few more, and then maybe we'll try to cover one more thing. So let's do 12 over 24. So for this one, what would be the largest factor that we could take out of this one? Let's see, someone said 3. So 3 would work, but it won't be the largest. Someone said 6. 6 would also work, but it's not the largest. So we got a 12, exactly, yes. So 12 is the largest we could take out of this. We can't go any bigger, because if we divided 12 by a larger number, we'd get a decimal number. So in this case, 12 is perfectly fine. So divide by 12, divide by 12, and we get 1 over 2. And always make sure you kind of like at the end, you look at things from a common sense point of view. Like 12 over 24 is, of course, it's 1/2. I mean, 12 is half of 24. So the answer of 1 over 2, it makes perfect sense. If you got an answer of like 1 over 100, hopefully most people would be able to see that that doesn't quite make sense if you look at what you originally had. Here's another one that's kind of an interesting one, 7 over 21. Now for this one, there's only a limited number of factors that you'd be able to take out. 7 is a prime number, so you could only divide either 1 or 7 into it. There's no point in dividing 1 into it because dividing by 1 never changes a number. So in this case, your only option is 7. So this one's actually, if you understand prime numbers, like you could kind of automatically deduce the answer for a lot of these. And someone correctly said 7 in the chat. So let's do that, divide by 7 and divide by 7. And we get 1 over 3. Okay, let's see. Let's keep, so it's 107. Geez, that went by really fast. Let's quickly squeeze in one more thing. Let's get rid of this because the next one is fairly straightforward. So I previously mentioned that we have something called mixed numbers, which is where you have a whole number component, and then you have a fractional component to that. And sometimes it'll be useful to convert that to a standard fraction. In this case, it'll be converted to an improper fraction because all of these will be greater than 1 because like they're mixed numbers. They're at least going to be 1 and a fraction or something like that. So how do we convert these to, I'm not going to say improper fraction because that's too hard to remember. I'll just say fraction. So how do we convert these to fractions? Here, I'll draw a little arrow and it'll say fraction. and it will say question mark to build up the suspense. Okay, so it's very easy, this process. Here's what you do. First, let's do the numerator, the top number. So how do we figure out the top number of our fraction that would be equivalent to this fraction? So what you do is you take 7, you multiply it by 4, and then you add 3. And that will be your top number. And it's always in that exact same order and that exact same format. It's always the big whole number times the bottom number plus the top number. So that will give us, so that's 28 plus 3. So that's 31. So that's the top number. And now for the bottom number, it's even easier. You just keep the same bottom number. In the original one, for the fraction part, the bottom number was 4. So you just do 31 over 4. And that's what you do for those. So bottom number stays the same. Top number has a very, very specific formula that you use for figuring out. Let's see. What else? So yeah, that's what you do for that. And if you wanted to put it in a generic formula, like if you had A and B over C, then it would always be A times C plus B, and then the bottom would be over C. So I guess that's technically a formula that you could use for it. So let's do one more example of these, just because they get pretty repetitive, because again, it's always just kind of the same thing over and over again. Let's do another one. And if I'm clearing these too fast, again, just keep in mind they're all in the PowerPoint. Like I have a second laptop set up, and I look at the PowerPoint even when I'm using a whiteboard. So 5 and 2 over 3. So in this case, for the top number, we'll get 5 times 3 plus 2, and the bottom will get 3. So the top is, so that'll be 15 plus 2, so that's 17 over 3. And in regard to the chat, just make sure you're giving everyone kind of room to answer the questions. Someone's doing some awesome answers, but make sure you spread the answers around. 17 over 3, correct. Let's see, what else can I say about these? Oh, we should look at yes, there's some common mistakes for this one. So people for this one, they get so focused on this top part because that's the most, I guess you could say, most complicated part. And they forget about the bottom part. So sometimes people will just cite the answer as being 17, which on the surface isn't correct, because how could 17 be equivalent to 5 and 2 over 3? Like, it's not the same. 17 is a lot bigger. So you have to remember the bottom part. You have to remember you're converting it to a fraction. So 17 over 3 is the correct answer. So that's one mistake that people make. Another thing you have to look out for is in regard to the top part. We got 5 times 3 plus 2. You always have to do the multiplication part first. So you always do this part first, and then you add the 2. So you got 15 plus 2, and then you get 17. So in general, you always do the multiplication part of an expression first, and then you do the addition part. Otherwise, you will get the wrong answer. And that's just bed mass, which will follow more in depth in chapter 2, I think. I think it's chapter 2. Okay. So there's a bunch of other, here, I'll switch back to the whiteboard, or to the PowerPoint. There's a bunch of other examples. So where are those? Here they are. And the answers are included. So use them for practice. I realize it's not super advanced calculus, but there's still common mistakes that everyone makes. And I don't think we have time for the next little topic. So I think we'll just call it a day. Maybe we'll look at banana for another minute. That's my pet snake for anyone who missed the initial beginning. Before we do that, does anyone have, oh, let me take the let me take the attendance. And as I'm doing that, let me know if anyone has any questions. Okay, so many people in this class. Okay, so I got this person, I got that person, I don't have that person. Everyone just bear with me. We got 2 Haleys, Holly, Isabel. Man, there's so many like names in here that are like names of actors or names of characters in movies for whatever reason. Julia, Megan, Riley, Steph. Did I get a Steph? Let's put Steph down. Steve. Like Steve Buscemi. Zoe, like Zoe Kazan. She's a good actor. I guess that's everything. Okay. Good, good. And if you could always check the attendance registry, and if I mistakenly list you as absent, just let me know and I'll fix it. And I think I'll post the first assignment as well. You won't be able to finish it, but it'll just be posted early just in case anyone wants to work on it as we go through the chapter over the next week or 2. And there won't be any formal due date yet. Again, it's just posted early. So let's see if Banana wants to hang out for another minute. Hi, Banana. What's up, buddy? Oh, there you go. There's Banana again. Where are you, buddy? There you are. Hi, Banana. One thing that makes me feel bad about Banana is that because he hasn't eaten in 2 months, he feels like an empty noodle. And it's like, oh, buddy, you got to eat something. You're an empty noodle. Here you go. Oh, I don't want to scare you. You're okay. So everyone say goodbye to Banana. And next time, I'll keep it a surprise for next time. Someone said we must do, someone said, oh yeah, your name, I already got that name. Yeah, I did some attendance in the beginning of class, so I already got most of them. So for the assignment, it'll just be posted early. And then once we finish chapter 1, then I'll formally decide on a due date. So yeah, at least with it being posted early, everyone has a couple of weeks to work on some of it, but don't worry about it. If you don't work on it, it's fine. I'll bring it up at the end of the chapter again. Ooh, one last cool fact about snakes is that snakes have legs. They actually have vestigial legs left over because they used to be burrowing legged lizards, and then through evolution they lost their legs. But if you look really closely, I haven't been able to find it on mine, but they do have 2 tiny claws that are technically legs that no longer work. So that's pretty neat. So hopefully everyone enjoyed the lesson and enjoyed Banana, and hopefully everyone is okay with the material so far. When is our next lesson? I think it's Monday. No, wait, I can't remember. It's at some point next week. So everyone, if anyone has any questions, I'll stick around for another minute. Otherwise, have an awesome weekend, and I'll see you next week. Bye.